Assalamu alaikum. Today we are going to present our capstone project, which is the wireless power transfer and charging system for electrical vehicle, which is supervised by Dr. Jawad Yusuf. So our problem statement is designing a high efficiency wireless power transfer system to charge the batteries for electrical vehicle. So we are required in this project to design a stationary wireless power transfer and charging system for electric vehicle. The efficiency of the wireless power transfer charger should be above 50%, choosing the suitable wireless power transfer technology for electrical vehicle. Finally, a mid and short range wireless power transfer. So now, moving to the consideration, as shown in this relation, the efficiency is directly proportional to the frequency and inductance of the coil and inversely proportional to the resistance of the coil. So we choose the coil with the highest inductance and the smallest resistance. And now this is our coil. Which from that sheet of a coil, we have 110 kilohertz and inductance which is equal to 25 microhertz and resistor and 65 milliohm resistor. So now coming to the proposed solution, we choose the inductive wireless power transfer technology to transfer the power. So when the AC current enters the transmitting coil, it generates an electromagnetic field. Then the electromagnetic field induces a voltage on the receiver coil. Now coming to the system view of our prototype. So firstly, the stationary wireless power transfer and charging system takes its power source from a DC power supply. Then the power source which is coming from the DC power supply is in form of direct current. So we need to convert it to alternating high frequency because the AC power is able to operate efficiently in the high frequencies. So the high frequency AC power is sent to the transmitter coil, and the transmitter coil generates a flux around the receiver coil. Lastly, the high frequency AC power is then converted back to a DC power source due to the load being powered by a DC power. Now coming to the transmitter side, we have a DC to AC circuit board, a microcontroller, and two ultrasonic sensors to sense when the car is at the top of the coil. And now my colleague Mohamed Al-Marzoughi will discuss the DC to AC circuit.
So coming to the inverter DC input voltage, we will start with the MOSFET driver, which is highlighted by pink, which is the IC control the gate of MOSFET in order to achieve an ideal switching at high frequency. And coming to the blue color, which is the high side switching MOSFET, and the orange, which is low side switching MOSFET, and the bridge. And after that, coming to the light blue, which is the bootstrap circuit, which is the diode and capacitor used to supply enough voltage to switch the high side MOSFET. Coming to the green color, which is the decoupling capacitor, which is the capacitor used to eliminate the noise and stabilize the voltage on the IC. And coming to the two signal, and we have two signals that generated from the microcontroller, and they are responsible for controlling switching of the MOSFET in the inverter. And moving to the microcontroller, we have the first picture is showing the microcontroller, and the second picture shows the coding that we demonstrate the operation of the circuit by the following code. By the microcontroller, we generate the two signals. Picture number 3 shows the two signal, which is the input of the MOSFET driver that control the gate of the MOSFET.
Now coming back to the receiver side, as shown in this slide, we have a receiver coil which is connected to the rectifier, and then the rectifier connected to the voltage regulator, which is connected to the measurement tool. And finally, from the measurement tool is connected to the battery. And now my colleague Amr will explain the AC to DC circuit.
Now, when we start designing the rectifier, we look for a diode with a small forward voltage to get high efficiency and small TRR. To rectify high frequency AC voltage, we choose 1N5820 diode, and here is the data sheet. After that, we connect the diode as shown. However, the output is 12 volt, where the battery charge on 5 volt. Thus, we add a regulator to step down the 12 volt to around 5 volt. After that, we have in the USB tester the receiver, the received DC voltage and current. Also, we calculate the received power equal 4.998, and for the transmitted power equal 6.664 watt. Thus, we get an efficiency of 75%, which is a success. And now after that, we will continue with my colleague Karim.
We also added a control system for the wireless power transfer system. The main job of this system is to ensure that the transmitter coil is on top of the receiver coil. It's actually like a brain of the wireless power transfer system. When the transmitter coil and the receiver coil are not on top of each other, the efficiency will be low and the receiver will be small and the losses will be high. However, when they are on top of each other, the efficiency will be maximum and the receive power will be large and the losses will be small. And here is the state chart and the code for the control system. Basically, we have two states, an ideal state and a charging state, and we will explain them in the next slide. And here's the code. First, the two sensors didn't detect any vehicle, or and even if the vehicle is not in the region. So the microcontroller will keep the system off. Now, in the second case, where it's the charging case, if the distance between the top sensor is 2 centimeter and the left sensor 7 centimeter, the transmitter coil and the receiver coil will be on top of each other. So the electric vehicle is in the specified region. Thus, the microcontroller will turn on the wireless power transfer system by triggering the relay and sending the signal 1 and signal 2 to the inverter. And now coming to the state chart and the code for the electric vehicle, here is the code. And we have two modes, which is the charging mode and the non-charging mode. In the non-charging mode, basically the LED, the red LED will be lighting and the car will be fast. And now in the charging mode, the car will be slow, and the blue LEDs will be blinking. Thus, we can actually precisely control the position of the electric vehicle on the road. The good of our design is the fact that if we just had a small edit on the DC to high frequency AC inverter, we can actually make it handle up to 1.1 kilowatt. A 1.1 kilowatt is actually sufficient to charge up a Tesla Model 3 car in 4 hours. Our proposed wireless power transfer system has a high charging speed where it charges our electric vehicle in 10 minutes. It's safe for the battery and it can be implemented in many places. Now, in conclusion, we built a stationary wireless power transfer system that contains a transmitter side and a receiver side, which is the electric vehicle. We also designed a control system to decrease the misalignment between the transmitter and the receiver.
Hi everyone, this is our prototype for wireless power transfer for electric vehicle. First of all, we have the inverter with microcontrollers, and here we have the transmitter, the receiver side coil with a rectifier inside the car, and we have here the transmitter side coil and two ultrasonic sensor. Now, first of all, after this, the two ultrasonic sensor will sense that there is a car inside the parking. The system will automatically turn on and it will start charging, as we can see. and thank you.